Good morning, everyone. Welcome back to class here on Monday for lecture 16 on syntheses. If you haven't already watched the exam solutions video, I mentioned on there that I have decided to give everyone an 8-point curve on the fourth exam. That means if you got a 92, then you end up getting 100 on the exam, so good job there. So this will be one of two lectures this week, synthesis today, and then tomorrow will be on alcohols, and that will be it for the rest of the entire class. You'll have Monday off. You'll have Wednesday off, as a break before the final exam, and then your final exam for both the lab and for the lecture are going to be on Thursday. Both will be posted at 8 o'clock in the morning, and both will end by 11:59 at night that same day. So make sure you get that done. They're both worth a lot of points, and they cannot be dropped. So today, at the end of the day today, you'll have a synthesis assignment that will be due the next day, and then tomorrow we'll do alcohols, and you'll have a quiz over synthesis, and then you'll have an assignment on alcohols. But then on Wednesday there will be nothing. Okay, that's actually assigned. There will be things that will be due by Wednesday, like in the morning your lecture assignments and the quiz. And then by the end of the day, one of your labs will be due, but there will be nothing new assigned on Wednesday, and no material on Wednesday to, give you a little bit of a break before the final exam. So let's go ahead and get started on syntheses. Let me switch my view there. Here we go. So, solving the problem of synthesis, right? The one-step synthesis. You got to provide the reagents. It's a straightforward when you know what your actual It's straightforward when only one reaction is needed. For example, here you've got a dihalide halogenation right here, right? So you'll need bromine gas to do this, right? So the point of this, though, is that you'll have to master all the reactions and the reagents required before you can tackle a multi-step synthesis problem, which will happen, okay? Which will happen. So it's critical to work through conceptual checkpoint 11.1 and 11.2 before moving forward. So do that, okay? Do that. All right, so so functional group transformation, right? That's kind of like the first thing we're going to talk about when it comes to synthesis. It's logical to review the two-step synthesis strategies from previous chapters. You saw that before too. We had the one where we did that was actually in the last exam. That one question where we ended up with halogenation and then elimination to get the alkyne, right? Remember that? So here we go. Moving functional group from one carbon to the next, right? So here we want to move a bromine from that carbon to this carbon. So the two steps that are required are an elimination step, which means you eliminate this bromine here, right? And then an addition step. So you add a bromine there, right? Okay, so here we need to obtain a ZZ alkene, right? A ZZ alkene, and choose a strong base accordingly, right? For ZZ alkene. So if you want a ZZ product, remember we have ZZ products come from slender bases, right? And Hoffman products come from what? Bulky bases. So you want a strong, slender base, right? Something like a sodium methoxide or something like that, a methoxide, right? Or ethoxide, something slender, and not something like tert-butyl butoxide, okay? And then the second step must be a Markov addition of HBr, right? So that's an easy kind of two-step synthesis to move a bromine from that carbon to this carbon, okay? Funny thing. I think I just said this. We can lay out all the reactions we know here where an alkyl bromides and alkenes are concerned, and then choose the reagents needed to yield the correct regiochemistry. So we start out with this bromine alkane right here, this alkyl halide bromine right here, right? And remember what I said, if you want to get a ZZ product, you need a slender base like sodium methoxide or sodium ethoxide. Here the book here, or the PowerPoint here, has chosen sodium ethoxide, right? It doesn't choose sodium butoxide. I mean, it doesn't choose tert butoxide though, potassium tert butoxide though, right? Because there you're going to get the the Hoffman product, right? you need to get the ZZ product, which is the double bond in the middle, right? And then you can do a hydrohalogenation, right, to get your bromine substituted at the most substitute carbon, right? So easy two-step synthesis. All right. So pay attention to the regiochemistry here, right? So we have an OH, right, a hydroxyl there, right, an alcohol, and we can use tosyl chloride, I guess it is, yeah, pyridine and sodium methoxide here, or concentrated sulfuric acid and heat, and that will also get us, right, a Hoffman product, right? Sorry, a ZZ product, okay? And then we can just do an acid catalyzed hydration, right, to get the alcohol substituted correctly there, right? Good stuff, right? You can also go backwards, of course. Once we get the ZZ double alkene right here, you can use the borane with tetrahydrofuran, hydrogen peroxide, and sodium hydroxide to get you back to the alkane, right? And then funny thing is, if somehow you ended up with or you had as a starting product the Hoffman, right, the Hoffman alkene right here, right, the alkene with the double bond at the end, you could go back. You could go backwards and get it back to the alkane by using the mercury method, the mercuration method, right? Or you can go down here with the tosyl chloride pyridine and the bulky base, of course, and that's what's going to give you the ZZ product. And then you can go and do the borane again, tetrahydrofuran, hydrogen peroxide, and sodium hydroxide, and you'll get the alcohol that's added over here, right? Added to the less substituted end over there. Less substituted end, and also on the Hoffman product side, right? So the approach must be modified for the analogous modification on an alcohol, right? Right? Because you can see each one of these reagents does a different thing that can get you closer to what kind of product you want to have. Okay. We also know how to apply a two-step strategy to move the position of a pi bond in an alkene, right? Where if you have an alkene here, a double bond here, you can do an addition reaction, right, and get your bromine substituted there, and then do an elimination. And once you do the elimination, you get your alkene there now, right? So first reaction, we need to add hydrogen bromide to the alkene, right? That was a hydrohalogenation reaction. And then for reaction 2, we need to do an E2 elimination. And when we do an E2 elimination, right, with the strong base, then we get our alkene there. Again, the reagents we choose depend on the regioselectivity we need. Okay, so here we go. Many choices. Okay, so here we are with our alkene right here inside of the ring, inside the cyclohexane, right? And we can do HBr with hydrohalogenation to get us this product here, right? Get us the bromine added to the most substituted side, right? And then we can do a terp-butoxide, right? And when we do a terp-butoxide, we'll get the I just said this on the previous slide, the Hoffman product, right? With the alkene at the end and not at the in the middle, right? If you go this way with the sodium ethoxide right here, you can go back to getting the ZZ product, right? But you didn't want to do the ZZ product. You were trying to get the Hoffman product, right? Okay. Or you can go from here, this double bond, the alkene inside the cyclohexane, and then do the hydrohalogenation in the presence of some terp-butoxide, right? And instead of the terp-butoxide, hydrogen peroxide, and instead of doing an addition at the most substituted carbon, it will go and do the addition at the least substituted carbon, right? Right there. And then go do the terp-butoxide again, right? And here you don't really have a choice, but your double bond will end up there, right? So we have no chance to get this far unless we can easily recall all the possible reagents, right, and the reaction conditions first. So a two-step sequence is needed to convert the alkane into an alkene, right? So we can do a cyclohexane right there, a 1-methylcyclohexane. And do a radical bromination, right? And that will get us this bromine as well. And then we'll do an E2 elimination, and we'll get this alkene right here, right? We'll do an elimination and get that alkene right here. And so we would then be able to convert the double bond into a single bond or a triple bond, right? So here is a triple bond, right? If you recall this from a few slides back or a few lectures back, right? We can go through and do some hydrogen gas and Lindlar's catalyst, right, to get us to the double bond, right? Or we can just go and do just platinum catalyst along with hydrogen gas and get us straight from the triple bond to the single bond. But if we want to go backwards, right, because here we have single bonds and we're trying to get to a double bond right here, you can use the single bond here, do the excuse me, the radical bromination right here. That's why it's bromine with some HV, right? That's UV light, right? And some sodium methoxide, and that will get you back to the double bond too. And then you can, of course, if you wanted to go even further, you can go straight back to being the triple bond again, using the bromine and carbon tetrachloride with the excess sodium amide and water, right? But in this particular slide, we're trying to get to the alkene. So it's just another way, right, of getting back to the alkene. Practice skill builder 11.1, changing functional groups. So far and for a little longer, we're just reviewing some of those different reactions that we learned in the previous chapter, so we can put it all together to do a multi-step synthesis. Okay. So for some transformations, it may be necessary to tamper with the carbon skeleton and add or remove carbons, right? When a synthesis requires a carbon skeleton to be altered, you'll need to be able to recall the reactions that add and remove carbons, right? Most reactions learned so far only change functional groups or change the location of it, right? We did have one though that would do movement of carbon, right? So again, so far we've only learned one transformation. Oh, I just said this. So far we've only learned one transformation that increases the number of carbons in a molecule, right? So here we have an alkyne, right? That's been deprotonated. This sodium alkyne molecule here that has 4 carbons. Okay, and then we have here a 3-carbon alkyl halide, right? And this can act as a base. This can act as a nucleophile, rather, right? Attacking that carbon there, and then we have a leaving group. And we've done a substitution reaction now, where we now have 7 carbons, right? And a sodium halide as a product, right? So for the time being, we know that this reaction will have to be used whenever we need to add carbons to a compound, right? We've also learned ways to decrease the number of carbons in a molecule too. Remember, we can have here 5 carbon atoms, right? This alkene, this one pentene. That's not right. Yeah, I guess it is 1 pentene. Or pen-1-ene. Sounds weird. Or we can use ozonolysis, right? We can use ozonolysis here along with some DMS, and we can go from 5 carbons to 4 carbons, right? Because DMS and ozone will make you an aldehyde, right? Along with more aldehydes, right? And you've lost a carbon, right? So in the future, we'll discuss many more reactions that alter the carbon skeleton. But for now, practice with Skill Builder 11.2, changing carbon skeletons. Okay? Whew. So to approach any synthesis problem, first answer these 2 questions. You have to answer the question, is there a change in the carbon skeleton? Is it gaining or losing carbons, right? And then, is there a change in the identity or location of the functional group, right? Solving a synthesis problem requires the recall of all the reactions learned and working through many example problems, right? So all those reactions we learned back in the radical reactions, and then in the alkynes, and then the addition reactions of alkenes, and then the alkyl halides, all that stuff. Excuse me. So for Skill Builder 11.3, we're going to propose an efficient synthesis for the following transformation. We want to go from this right here, this alkyne, terminal alkyne, to this alkene, right? So let's answer the questions. Is there a change in the carbon skeleton? Well, the answer is yes. The starting compound has 5 carbons, and the target compound has 7 carbons. My head's blocking it right there, but let me show you. Right there, see, there's definitely 7 carbons. So the answer to the first question is yes. I'm trying to bring myself back. There we go. Okay. Question 2. Is there a change in the identity of or the location of the functional group? Well, yes. An alkyne is a functional group, and it has turned into a transalkene, but the location hasn't changed. It remains between carbon 4 and 5, right? Carbon 4 and 5. So really, the only thing we need to do here is change an alkyne, right, onto to an alkene, number 1, and then also we need to add on 2 more carbons. Okay, so the synthesis needs to accomplish the following, which is what I just said. I'm going to say it again. A triple bond must be converted to a transalkene, and we have to add 2 more carbons, right? So what reagents and reactions will accomplish these tasks? Think about it, okay? And what's really helpful with that is using those charts that I show you at the end of each lecture that have the little arrows, that you know, the single molecule in the center and all the arrows and all the different reagents and stuff. That's super helpful, okay? So here we go. 2 carbon atoms can be introduced by alkylating the starting alkyne, which gives you the correct carbon skeleton. So here we're going to use sodium amide, right? Sodium amide. And then we're going to use ethyl iodide, I guess that is, right? And the reason why we're using ethyl iodide is because ethyl iodide is a good, not ethyl iodide, but iodine is a good leaving group. And when it attaches itself, it'll leaving behind the ethyl group, as you can see here, right? And then we want to do a trans, let me block my, there we go. We want to change an alkyne, right, to a transalkene. Easiest way to do that is to do some dissolving metal reduction, right, with some liquid ammonia, and we can get there, right? So it's a two-step it's a 2-step, but actually it's 3 reaction synthesis. Okay, it's a 3 reaction synthesis. I don't know why I'm going to say this again, but I guess I'll say it again. It's extremely important to match each reaction in the multi-step synthesis, right? Merely listing the reagents together is not sufficient. Oh, I see. Yeah. So it's just telling you this again, right? It's telling you this again. So really, you shouldn't be doing it this way, right? These 2 need to go together first, right, on one reaction arrow, right, and then this one needs to go on its own reaction arrow. And so when it was saying that it was a 2-step process, it's actually a 3 reaction synthesis, right? That's reaction 1 there, which is the sodium amide, does the deprotonating, right? And then the nucleophilic attack happens with the ethyl iodide, right? And then that's the second reaction, but the first step is both of these together. And then the dissolving metal reduction is the sodium and the ammonia, right? So you've got to make sure you keep those straight. There are more examples in practice. So there are more examples in practice. The skill. That sentence makes no sense at all. Anyway, Skill Builder 11.7 for identifying reagents in Wiley Plus. So there's this thing called retrosynthetic analysis. And in retrosynthetic analysis, simply put, this approach means we solve the reaction sequence in reverse order. We begin by solving the last step of the synthesis first. Still, we need to ask the 2 same questions, right? Is there a carbon skeleton that's changing, right? And is there a functional group changing or moving, okay? So number 1, Analyze the structure of the reactant and the product. What are the functional groups that we are dealing with? So here's our thing, okay? Perform the retrosynthetic analysis for the following synthesis. Is there, here we go. Is there a change in the carbon skeleton? Actually, let's see. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Nope, no change in the carbon skeleton. No change there, okay? Is there a change in the identity of the functional group or its location? Yes, there is. An alcohol is being converted into an alkyne, but the position hasn't changed, okay? The position hasn't changed. Okay, so let's focus. Let's work backwards here and focus on the last step. What reactions do we know that can be used to make an alkyne, right? This step right here, to make an alkyne. Well, an alkyne can be installed on this carbon skeleton by elimination of any of the following 3 dibromides, right? This vicinal dibromide is the only one we know how to make, though, right? Okay, so recall that retrosynthetic synthesis arrow, right, is used to indicate the step of thinking backwards that we use for the last step. So this is our retrosynthetic arrow, okay? So this alkyne right here can be made from this dibromide here, right? Can be made from this dibromide here. So we have to just solve. So we have just solved the last step of the synthesis by identifying the reactant that we can use to produce the final product, right? And so let me move my head out the way. Here we go. We have an alkyne there, right? And we can use excess sodium amide and water, right? And that will change the vicinal dihalide right there into this alkyne, right? So that's the first step of the retrosynthetic analysis, right? That's the first step of the retrosynthetic analysis. Now we can continue to work backwards another step. The vicinal dibromides or dihalides, right, are made by an addition reaction to an alkene, right? We already knew that from addition reactions of alkenes, right? So this alkene would need to be, this is the alkene that we would need to make the dibromide, right? So you already know then that this will be the structure that comes before the formation of the dibromide, right? So recall that Br2 is needed as a reagent for this reaction. So we've already solved these 2 steps right here, right, of the retrosynthetic analysis, right? The last 2 already, or actually this would be the last 3, right? The last 3 structures and the last 2 reactions required, okay? The alkyne can go to the retrosynthetically go to the bromine, the dibromine, right, or dihalide, and then to the alkene, right? So now, all we need to do now is figure out this step. How do we get an alcohol, right? How does an alcohol change to this, the alkene? So at this point, we should recognize that an alcohol, right, can be converted into an alkene via dehydration and elimination reaction. How do we do that? Well, the first step is to convert the alcohol to a tosylate and then eliminate it with a non-nucleophilic base, right? So here's our tosyl chloride to make a tosylate with a pyridine and the DBU, DBN non-nucleophilic base. And we've completed the entire retrosynthetic analysis. Good stuff. No, I never brought myself back. I'll bring myself back on the next slide. There's even room for me to come back there. There we go. Okay. So overall, here is the multi-step sequence, right? Beginning with this alcohol, we do the pyridine. We do the pyridine with the tosyl chloride, a bulky base there, terbutoxide. We do some bromine bromination with carbon tetrachloride, then sodium amide, right, to do the act as a base there, right? Excuse me, and some water. So to ensure that this is correct, we should go work out each reaction and make sure the correct regio and stereoselectivity, right? Make sure of that. So practice with Skill Builder. 11.4, multi-step synthetic analysis. There's also green chemistry considerations. We all got to be environmental these days, okay? So green chemistry refers to reactions that are more environmentally friendly, and it has these 7 guiding principles, okay? Prevent waste, use less hazardous substances, use safer solvents, right? And then maximize the atom economy. Use reagents where all or most of the atoms of the reagents are incorporated into the product. So very, very little waste. Very little waste. So consider these 2 reactions that we already know. Convert an alkene to an alcohol, right? We have oxymercuration, demercuration right here, okay? And in that reaction, we were able to change this methyl group to this alcohol right here, right? Or not change it, but add an alcohol to it, right? But this is very poor atom economy, okay? The atoms, all the atoms that are in red are waste material, right? Waste, all that stuff is waste, okay? But you could also do an acid catalyzed hydration, right? Catalytic amount of acid, and then some water there, and look what we have. We have our same product. And every single one, except for that catalytic proton, is used. Every single atom. Every single atom is used. Man, that's some green chemistry right there. Let's reduce our carbon footprint, right? Nice stuff. So, there are more guiding principles. I think that we only went through the first 4. Next, use catalysts rather than stoichiometric reagents, right? Because you don't have to use as much catalyst. Catalytic amount always means very tiny amount, right? Make it energy efficient. Reactions performed at room temperature are way more energy efficient than those that require heat, like things that require refluxing or distillation, that kind of thing, right? And then renewable feedstocks, using sources such as grains, corn, and sources of carbon opposed to petroleum. Man, we're totally going, environmental here. We're going to be using it's like when you, so recently, Lego, I told you guys before that I'm like a huge Lego fan. I build Legos all the time. And recently, Lego normally is made of ABS plastic, right? What does ABS stand for? I can't remember, but it's a very brittle, not brittle plastic, but it's very, it's a strong plastic anyway, right? But it's not very environmentally friendly, and not to mention the fact that it's toxic too, like the fumes. I use ABS when I do not plastic, when I do 3D printing. I'll use ABS to do 3D printing, and the smell when you melt it, so you can mold it and stuff and do the 3D printing, smells like, it smells like, burnt butthole. So I can't imagine that the fumes are very safe for you. But, so the same plastic is used to make Lego bricks. But recently, Lego has been trying to go green, and so now they're making their plastic bricks all out of plant plastics, right? And so that's what they're talking about here, using a source of carbon as opposed to, using sources such as grains and corn as a source of carbon as opposed to petroleum, right? So that's what Lego's doing. They're trying to. And let me just tell you, their Lego bricks that are made of plant plastics, they definitely feel a little different. They look a little different too. They're not quite as shiny. But I'll sacrifice some of my favorite hobby for the environment, I guess, right? So the key here, right, is to actually make it easier on yourself, is to actually organize the reactions into 2 types of reactions, okay? Reactions that alter the carbon skeleton, meaning adding or subtracting carbons from the carbon skeleton of the reagent, right? And reactions that alter the functional group, okay? As more reactions are learned, add them to the list, the appropriate list, okay? So a great way to practice synthesis is to design your own problem, right? Start with a relatively simple reactant compound, choose a reaction, write out the reagents, and then predict the structure of the product, right? Repeat step 2 a few more times. Take out all the intermediates and reagents so you don't give away the answer, and swap problems with your classmate, which you can't really do that very well right now in these times that we have when the class is completely online. But I'll help you out with that by assigning you some assignment problems. Okay? So let's take a look at this one. This process will help you think about syntheses in new ways, right? So here's an example starting with acetylene, okay? Acetylene, the alkyne right here, reaction 1. Choose a reaction for an alkene, right? And then write out the reagents and then draw the product, right? So that's what we have here, okay? That's what we've done here. repeat steps 2 a few more times, right? So a couple more practice problems, right? And then take out all the intermediates and reagents so that you don't give away the answer. And then swap the problem with the classmate. In fact, I've done this to you already before in a few test questions and a few assignments. On the Blackboard assignments. So you don't have to do this because I've already done this for you, right? But we mean for these PowerPoints to be doing. We've been doing this in class. Okay. Okay. So just remember, right, that there's always more than one way to solve one of these synthetic problems. Just an example, right? We can use boron trihydride, or someone else would call it borane, and tetrahydrofuran along with hydrogen peroxide and sodium hydroxide. And you can get this. You can change this alkene and hydrate it to an alcohol, right? But you can also use hydrohalogenation, right, along with hydrogen peroxide, along with sodium hydroxide, and get the same alcohol, right? So in general, a chemist's goal is to find the fast. Oh, it's blocking my view, and it's also blocking your view. In general, a chemist's goal is to find the most facile synthesis, and generally having the fewest steps, right? Bring myself back. So that actually ends today's lecture. I know it was a short one, but tomorrow's will be much longer. So again, it's kind of like your little break in between until you get the really long lecture tomorrow about alcohols, and then your break before the final exam. So you'll have a question. You'll have an assignment assigned today that will be due tomorrow, right? That's going to be synthesis problems, just like I went over in there, right? Since you guys can't go and swap problems yourselves, I will be the person doing the swapping for you in the form of Blackboard assignments, okay? They'll be due tomorrow by June 29, 2021, right? In the morning at 7:59 a.m. There won't be a quiz assigned today, of course, because we never have quizzes on Mondays. But the biggest thing is a reminder here is that your final exam is on Thursday, July 1st. Make sure you're ready for that. Your lab final is also that day too. Make sure you're ready for that. And good luck. I will see you tomorrow for our alcohols lecture.